Just a couple of things. You don't need to know any combinatorics for this video. And although the first few minutes of the video seems irrelevant, I promise you everything will come together at the end, so stick with me. Take a look at this decimal. You might recognize Fibonacci sequence in the beginning, but then you see 9 and stop for a second. However, in the Fibonacci sequence, the next few numbers are 8, 13, and 21. And actually, we can imagine the 10th digit of 13 is carried over to the previous digit of 8, making it 9, while the 10th digit of 21 is carried over to the previous digit of 3, making it 5. So basically, this decimal is the shortened form of this series. Before we do anything, however, we want to learn the technique to do this, using another example, the geometric series. Geometric series is simply the sum of an infinite geometric sequence with the first term a, and the next term is the previous term multiplied by the common ratio r. Before we move on, we need to note that r must be sufficiently small in magnitude for this series to converge. In this case, the absolute value of r has to be smaller than 1 for this series to make sense. To calculate this series, first we denote the sum as s, then multiply by r, and subtract the second equation from the first. Then we would have this formula, which you might have seen before. So can we pull a similar trick on this series that we have been interested in? Let's see. To save space, we generalize this a little bit and replace 1/10 to be x. That means we have this series. Again, the magnitude of x has to be sufficiently small when we do a generalization like this, but 1/10 definitely falls within this range. Like what we did before, multiply both sides by x, subtract the second equation from the first. Although we don't have everything cancelled, the series after the x term is actually x squared times the series we want to calculate itself. So by rearranging, we have the ultimate formula for s, which is pretty neat. Remember that we replace 1/10 by x, and so now do a substitution, and we finally get the answer to be 10/89. Of course, you know that the real purpose here is not about finding the value to this fraction, but just look at what we have derived together using a similar technique. Do you think these two expressions are somehow similar, or even related? If we replace a by x and r by x plus x squared, then the two expressions would be identical. That means we should have the original series with Fibonacci coefficients equal to a geometric series with first term x and common ratio x plus x squared. Let that sink in for a minute. But why is this the case? I mean, we have done algebra to see that this is the case, but are there any other ways to see the equivalence of these two series? Here is what we are going to do. In this series, we are going to find the coefficient of x to the power 10, which we abbreviate as c with subscript 10. To do this, we find out all the terms that contribute to any x to the power 10 term. We should expect that the number of x to the power 10 terms would be exactly the 10th Fibonacci number, which we abbreviate as f with subscript 10. Remember that the method we follow can be generalized, and we just use a convenient number to illustrate the process. Therefore, what we actually aim to do is to prove the two defining relations for Fibonacci numbers, which are that the first two coefficients are both 1, and every coefficient thereafter would be the sum of the previous two. So first off, this is the list of terms in the geometric series that could produce the x to the power 10 term. For the first thing here, we first write it like this. In the fully expanded form, each term is formed by choosing either x or x squared in each bracket, and then multiplying them together. Then multiply by x altogether. So that means we need to generate the x to the power 9 term with the brackets. This can be done by choosing the x squared term in 4 of the brackets. For this reason, let's denote the number of ways to choose 4 out of 5 objects as shown, and we call it 5 choose 4. Now for the second thing, we again write it like this. Then again, we want to generate the x to the power 9 term within these brackets. That means we need to select the x squared term from 3 of the brackets. Since we are choosing 3 out of 6 objects, we denote this as 6 choose 3. In the similar spirit, we can also write down the number of x to the power 10 terms contributed by other items on the list. You might be surprised at this notation here, 9 choose 0. But there is always only one way to choose 0 objects out of any number of objects, which is not to choose. So it is by convention equal to 1. However, our objective here is not to calculate all these numbers explicitly, because that will not generalize the argument well. And I specifically said that you don't need to know combinatorics beforehand, so here is what we're going to do. Let's say we choose our objects out of n. The selection can either contain the orange object or not. If the selection has to contain the orange object, then we are choosing r minus 1 objects only, because one object has already been chosen. And this is chosen out of n minus 1 objects, because again, one object has already been chosen. But if the selection does not contain the orange object, then we have the freedom to choose all the R objects. However, since we do not want to touch that orange object, we only have n-1 objects to choose from. Since the orange object is either chosen or not chosen, we have this relation between the something choose something. Remember that we have this relation we derived together. In a very similar fashion, we can also derive the coefficient of the x to the power 9 and x to the power 8 term. Using the relation we have just discovered, we can check that C9 and C8 add up to C10. Here is just one small caveat, because we don't directly use the yellow result below. However, they are actually both 1, as discussed previously. So we can safely say that C10 is the sum of C9 and C8. You can easily generalize this argument. There's just one small thing to consider. We need to prove that the first two coefficients are 1. Then we can finally say that all the coefficients here are Fibonacci numbers. This is relatively easy, because it is very obvious that only these two red terms would contribute to the x and x squared term, as other terms in the series produce terms of higher powers. Essentially, we have proved that the coefficient of x to the power n term is exactly the nth Fibonacci number, offering us another, not entirely algebraic proof for the equivalence of these two series. If you want to make the relationship between Fibonacci numbers and combinatorics a little bit more explicit, we can generalize what we did here, and to write Fibonacci numbers as a sum of these something choose something. In combinatorics, we call these binomial coefficients. So we have successfully discovered the relationship between Fibonacci numbers and the binomial coefficients. Here is something that I wanted to say last time but didn't because it was filmed already. As a content creator, I highly value your feedback and would like to gear more towards you, but I don't really know all of your math levels. For example, if most of my viewers have already learned calculus, then I can skip those parts and produce more advanced contents without worrying. On the other hand, if most viewers do not know a particular topic, then I know that I need to briefly introduce that topic before moving on to the focus of the video. So I hope that you could fill in the Google form linked in the description to help both you and me by helping create content more catered for you. Subscribe if you want more of these math videos. See you next time!